Hi, in this section we will talk about the operational amplifier. First, we're gonna give some introduction. Then we'll talk about a little bit ideal operation amplifier. We'll talk about the relation current and voltage on the operation amplifier. We give examples. These two examples, one is in inverting amplifier, the other one is non-inverting amplifier. So you can see the difference. The operation amplifier, which is we call op amp, is an electronic circuit. It's just like behaves as a voltage control voltage sources. Okay, the typical shape is a chip like this. We have 8 pins. You can have a different pin connection too also. But this one we have here one inverting amplifier, which is pin number 2. We have non-inverting amplifier input, which is pin number 3. We have negative source and positive source. Negative source is pin number 4. Positive source is pin number 7. Then we use output as number 6. We don't consider the other inputs now. So when you look at here, you will see we have V positive, which is non-inverting input, V negative, one inverting input. We have source, negative source, we have positive source, and we have output. Typical operation amplifier is we use mu A741. There are different numbers, names too also, but typically we use mu A741 in our class and lab. Okay, one more time. The typical sample, circuit operation amplifier sample, we have V in, negative and positive. We have supplies, negative, positive. Then we have output. If you look at the equivalent circuit of operation amplifier, we have resistance value between two inputs. Okay, we have output resistance value at the output. We have voltage control voltage source in output side here, GV in. V in is the difference between two voltage sources, input, two voltage input. So we have Vs negative and Vs positive. We're gonna look at the internal value or equivalent circuit later one more time. These are the assumption we use. Number one, we say gain is large, very large. That's why we can say open gain, which means infinitive gain right there. The gain is V out over V in basically. The input impedance R in or resistance value equal infinitive. Okay, so there is no current. That's why current is 0 over the V in and going to input and input. We have output voltage, the input offset voltage is equal 0. We're gonna come this two term here. You will see here one of them is IN equal IP equals 0. The other one is input voltage is 0, means VN will be equal VP. The output voltage range is infinite again, but actually real depends on the output, the source values, the supplies voltages. And we said bandwidth is infinite, and we said also infinitive phase also infinitive right there. We can say Rout output impedance is equal 0 and noise level is equal 0. And gain again one more time, gain is basically sometimes we show A, sometimes we show G, but that is infinite open gain here. This is typical and ideal one. Gain 10 power 5 to 10 power 8, which is the ideal one, we call infinitive. Input resistance 10 power 5 to 10 power 13, we call infinitive right there. Output resistance 10 ohms to 100 ohms, we call 0 basically. The power supply, the range is power supply is 5 negative positive 5 to negative positive 24 volt range. When you look at the circuit operation amplifier, current goes from the sources, current goes from the inputs, current goes out from right there. But again, when you add them together here, it will be equal 0. That makes sense because KCL. But I1 and I2 or IP or IN will be equal 0. These are will be equal 0 because the open means here there is no current go inside here. So we're gonna look at this equation one more time later. That's why we can use KCL. Um, Also, this is shows the V input to V output graph right there. We're trying to work in this range here, this linear area. Otherwise, the output will go to um, saturation in VCC or negative VCC right there. So we're trying to work in this range right there. A mathematical way we can show this one again. Gain is less than negative VCC. We're gonna stop in the VCC. Gain is larger than positive VCC. We're gonna stop at the VCC. Between this area, we have linear input-output relation. We talked about before the input, the voltage difference between VP and VN minus VN is close to 0, which is ideal one equals 0, then VP equal VN. This is number equation 1. Because of gain is large, then when you have output, you not have more than supply. If you want to work in a linear area, that's the one you're gonna have it. Okay, that's the question. That's the equation 1. The equation second one is because of there is no current, typical input resistance is large, then we're gonna say IP equal IN. So we can use the KCL rest of them. Let me look at here example here. I'm trying to finish this one in 10 or 15 minutes. Let's see here. If we have this circuit and I'll assume first one is VB equals 0. Okay, so we have VA right there. We have V out right here, and we have feedback 100K, and we have input next to our input voltage, input resistance value. We have it. First thing, number 1, do we know VP? Yes, VP equals 0. And we know that VN will be equal VP. That will be equal 0. Okay. Then we're going to write KCL in this node right there. If I write that one, can I say that one is equal like this? VA minus VN divided by 25K. Then I will say plus because current goes in. I will say V0 minus Vn divided by 100K equals 0. There is no current goes in here. That one is equal 0 right there. Okay, now what's going to happen? I know that this is equal 0, and I know this is equal 0 because that's grounded. Basic, not grounded actually. VB equals 0. That's why. From here, I can say V0 divided by 100K will be equal negative VA divided by 25K. So if I put 100K, I'm sorry, 100K right there. So V0 will be equal negative 100K divided by 25K times VA. From here, negative 4 times VA. If VA equal 1 volts, then this will be here negative 4 volts. What happened? We apply 1 volt, we get output negative 4 volts. First, amplify gain. How much gain you have it? The gain is this term here. This is the gain you have right there. Gain is this one, which is 4. Okay? In this case, the gain is depends on your feedback resistance and this input resistance right there. Okay, gain is also inverted. That's why this is inverting amplifier. Let me show you another example here. If you have 2 sources, what's going to happen? This case we have VB and we have VA right there. Simple again. We're going to say VB equal VP. So will be equal VN. So if I want to write the KCL again, I'm going to show this one here, this direction. I'm going to show this direction here. I will say directly KCL, not at VN. I will say this one here, VA minus VN divided by 25K. I will say plus V0 minus Vn divided by 100k equals 0. So Vn is equal Vb. I'm gonna put them right there. I'm gonna separate them. I'll put like this. I'll say Va divided by 25k minus Vb divided by 25k plus V0 divided by 100k minus, I will say Vn, which is Vb divided by 100k equal 0. Va, Vb, okay. So I'm gonna leave here V0 divided by 100k alone. I'm gonna put the other side. Okay, I'm gonna have negative here 1 over 25k Va. I'm gonna put plus here 1 over 25k plus 1 over 100k times Vb. If I leave V0 alone here, then 25, oh, this is 100k, this is 100k. Okay, this will be here negative 100k divided by Va plus this will be 100. Let me make clean this one here. Okay, negative here 100k divided by 25k Va plus I'm gonna have 100k divided by 25k plus 100k divided by 100k times Vb here. So the output is actually depends on two gain here. One of the gain right there, one of the gain right there. And first gain is negative, and negative. Second one is positive. You can see here from here. I can put the values. I can find the final value directly from there easily. What's gonna happen if you have a typical equivalent circuit? What's gonna happen? I'm gonna look at a simple circuit here. If you have this circuit right there, we did this one here. When I look at the V0 from here, negative RF divided by RI times V input, which is this case is 100 divided by 25 k times 1 negative 4 volts. If we put the typical equivalent circuit of operation amplifier to find the real value, more equivalent value, I'm gonna look at this one as like this here. This is my operation amplifier pretty much right there. So in this case, we're gonna write two KCL. One is this one here, one is this one here. So we're gonna write KCL. Number one, first one, I can say this one here. One, because pen is giving me a hard time. 1 minus V1 divided by that one is 25k negative V1 divided by R. R is 2 mega. This case, let's say assumption. Then I will say the other one's going out. Okay, I'm gonna say going out negative. I will say V1 minus V0 divided by 100k equals 0. This is my first equation. My second equation will be this one here. Why we need a second equation in this case? Because there is a V1 and there is a V0. We need to have two equations to find two unknowns. Second equation will be this. V1 minus V0 divided by 100K. Then this going out, I'm gonna have V0 minus A times VD divided by 50 ohms. And here VD is this one here. VD is given to you as, did I give it to VD? VD will be equal negative V1. Okay? So if you want, you can simplify this one here, putting the V1s together. So I'm gonna have negative, negative, negative. I'm gonna have negative sign 1 over 25K plus 1 over 2 meg plus 1 over 100K V1 minus minus positive 1 over 100K V0 will be equal 1 over 25K. That's the first equation. Second equation, I can do similar way. I'm gonna do this one is like this here. V1 divided by 100K minus V0 divided by 100K minus V0 divided by 50 minus minus positive another minus right there. I'm gonna have here another minus A times V1 divided by 50 equals 0. If you put the V1s together here, I think we have 1 over 100 minus A times 50. This is negative. V1. Then V0s, I'm going to put a negative sign. I'm going to have 1 over 100K minus 1 over 50 V0 will be equal 0. So we have here two equations, two unknowns. We can use our calculator to find the values. When you find the values, and again, in this case, I believe for A, I use 10 power 6. 10 power 6 here value. When you find out the values like this, you will see V0 is coming here negative 3.96. The ideal one, we find V0 equal negative 4 volts. What is it different? How much different we have? I think less than 4%. So ideal one is much simple to find out and not too much different. You can see here that you don't have to do this many steps right there. Let me give you one more example, another example here. This case here, I'm gonna give example a little bit different. Maybe I can give this example first, then I'm gonna jump to one of the final question right there. This case, if you look at here, input is in the VP, output is delay, output is coming back to VN connection right there. So first thing, VP equal V1. That means VN equal VP, which is equal V1. Okay, next step. We're gonna write KCL right there, KCL. I will say 0 minus Vn divided by Rs. I will say here plus V0 minus Vn divided by Rf equals 0. If I put a V1 and the Vn, I'm going to have this equation. Negative V1 divided by Rs, positive V0 divided by Rf, negative V1 divided by Rf equals 0. From here, V0 divided by Rf will be equal negative, negative is going to be positive right there, 1 over Rs plus 1 over Rf V1. And if I put the RF the other side, I'm going to have V0 will be equal here 1 plus Rf divided by Rs times V1. So this is the equation, we have it. Then output is again depends on the gain right there. Gain is this one here, and positive 2. That's why they call this one as non-inverting basically. I'm gonna jump a couple of steps. I think similar one, only we have values. I'm gonna look at this one here. this is the example, maybe a little bit different. But again, same rules we have it. The rules is this: VP equal VN, number one, IP equal IN equals 0, number two. So can I find VP value? Can I say voltage division? Yes. So number one, can I say VP? I'm going to change the color here, like blue. Okay. VP will be equal voltage division. I think easy, I can write 8K divided by 4K plus 8K times 3 volts, which will be equal, I think 2 volts right there, if you do it. So I'm gonna write KCL at Vn. So KCL at Vn. Let me write the first equation right there. We'll see what's gonna happen. And one of them is going down. That one is negative Vn divided by 2K. The other one going in, positive V0 minus Vn divided by 5K equals 0. Fine. So do we know Vn? Yes, because Vp equal Vn, right? So minus, I can write the Vn and put the value right there. I'm gonna do like this here. I'm gonna have minus Vn divided by 2K plus V0 divided by 5K minus Vn divided by 5K equals 0. So from here, V0 will be equal, I will say 5K over 2K plus 5K over 5K, then Vn here, which is Vn equal 2 volts. So one more time, V0 will be equal here 1 plus 5 over 2. Then 2 volts right there. Did I make a mistake? No. So this will be equal again. If I put there 2, I'm gonna have 10, 15 divided by 2. 15 divided by 2 times 2 volts. I made a mistake. Oh, no. This is wrong. Okay, I got it. Can I erase one here? This will be here 7 over 2 times 2, which is equal 7 volts. This is our final answer. Again, not too much different than KCL, KVL rules. Only we need to apply these two terms to find out the V output directly from here. This is the end of the section.